Thanks so much, and super happy to be speaking again at Scale by the Bay for the second year in a row. And with that, I will just jump straight into things. So quick agenda. Yeah, we're going to be doing some live coding. Always high risk, especially with timing. So going to try to get everything in the 30-minute session. So we'll start off with a very kind of quick intro, just about me. We'll go very quickly into just some quick thoughts, musings I have on stateful versus stateless. Then we'll introduce, for those of you who are not familiar, just kind of Akka and Akka streams. And when I say quick, all of those things are going to be very brief. Just want to make sure no one gets kind of left out. And then we'll jump into some design patterns and the live coding session. So with that, let's jump right into it. So I actually recently got a nice promotion. So I'm actually the engineering manager for our portfolio and data team at M1 Finance. So I am also a certified sommelier. So whether you want to talk about reactive things or food and wine, I am absolutely in. Shameless plug for M1 Finance. We are a investing app. So we have a checking account. We have an investing app where you can buy and sell securities, margin lending, and we also just released a credit card very recently. So thank you for indulging my shameless plug, but yes, it is an excellent company to work for, and all of our backend services are built using Akka, Lagom, and Scala. So it's a very cool tech stack to work with. So now my musings on stateful versus stateless. So simply put, I like to think of, there's two kinds of data that is super prevalent in building distributed applications. So you've got data in motion, something like we're consuming messages from one place, they're moving around our system between, different functions, different services, different messaging queues, and, they're kind of ethereal. They'll come through the system, and then at some point they're gone and they're done being processed. Then we also have data at rest. So this is typically when people think of state. And so state can be in memory, or it can be durable. There's a lot of different kind of options for state. It can be sharded. It could be all in one place. It can be in a data lake somewhere. But when we think of stateful streaming, it's the idea that how do we take this moving data and cross-reference it or apply it to this stateful data and do something kind of useful and interesting with it. So it's been especially in distributed systems or large scale systems, it can sometimes be complicated, and tying these knots through streams and stateful services can be a little complicated. So I just wanted to do this session so that we can talk about some of these patterns and some of the lessons that I've learned over the last couple of years, really using Akka in production. With that, what is Akka? Akka is this actor model designed on Scala, kind of with a Scala first mentality. And it's exceptional for building distributed systems. The first piece of it we're going to talk about is Akka Streams. Akka Streams is this really nice back-pressured reactive stream implementation where you're able to kind of take these operators and plug them, one by one, and do some really creative and interesting message processing and asynchronous operations, multi-threading with Akka Streams. And so when I say back-pressured, what that means is the idea that downstream operators do pulls upstream. That's this little arrow here. So if our sync has time or has nothing to do, it'll pull from the operator before it to say, hey, give me something to do. And same thing with this flow and all of them. I really like to think of it as a bunch of people sitting at kind of an assembly line, and the person at the end, if they have nothing to do, will look to the person to the left of them and say, hey, give me something to do. And everyone down the assembly line is kind of operating in that same manner. And when someone needs a request, they'll look upstream, and then work will come down, you do your work, and then you push it down to the next one. The reason why that pattern is really useful is so that no specific operator gets overwhelmed. You wouldn't want to be in a situation where your flow right here is a little bit slower than your source. And so the source can push data in at 10 messages a second, and the flow can only process them at 1 message per second. Eventually memory, there's some buffer here, memory fills up, and we have some sort of outage. So Akka Streams is really great, and we will be writing some of that today. The other big tool that we're going to be using is called Akka Cluster Sharding. So Akka itself has this idea of actors. And so actors can represent state or work. And with Akka cluster sharding, we're able to spread these actors around the cluster, but still have access to them, as if they were local. So we could generate an actor that is collecting data for Amazon or Tesla, and we can guarantee that there will only be one example of the Tesla or Amazon actor in the cluster. And if we're doing over here and we process some message that has to do with Tesla, we can still forward that message over here and get an acknowledgement that it's been processed, and then finish processing it. So that's what we're going to be doing today. But Akka cluster sharding and Akka Streams, really great tools to bring into your design next time you're building a greenfield application. So the use case, we're going to build an app that is processing real-time financial data. So we're processing real-time finance quotes, and this is what our case class quote message looks like. So we've got an ID, a company, and then the field we're really going to be using is this last. So what is the last market price for this share? And then we have a timestamp. And so we're going to process these messages. And so this is our stream of data. So we have a constant stream of quotes coming into our system. And then where the state comes in is we're going to be windowing this information and then trying to make some sort of calculation. And for this case, what we're going to do is we're going to calculate in this window of 10 seconds, what is the max price we've seen? What is the min price we've seen? And is this a upwards or downwards percent increase or decrease, and whether or not that breaks some sort of threshold. So the first model we're going to kind of work with is, well, all the models for today are going to be pulling data from Kafka. So we've got partitioned data in Kafka. The data is partitioned by the company. So, everything for Amazon will be on one topic or one partition, and then everything for, GM and Apple will potentially be on other ones, but we're partitioning by the company. And then we have an Akka Stream instance that is reading this data. For this example, we're running it locally. So we've just got one node that's running all of this. So the first example, Stateful Mapkincat. When we're building Akka Streams, you can see these boxes here, and each box is kind of a different Akka Streams operator. And Stateful Mapkincat is a very cool tool for being able to pull in a few messages as state, and then potentially emit one or more messages downstate when you're done, or downstream when you're done processing that message. So what we're going to do is we've got a stream of all sorts of different companies coming into our application. We are going to group by the company. That way we end up with a substream, each substream representing only one company. And then we're going to window that information in our stateful Mapkincat, do our calculations to figure out what the percent increase or decrease is, and then push that data downstream, merge these substreams back together so we end up with kind of one outlet. And then we'll be able to send our alerts to our users, whether or not their securities are increasing or decreasing in price. So now for the fun part, let's write some code. So jumping over into IntelliJ. Boom. So I really wanted this session to be like completely from scratch, writing absolutely everything. Sadly, with 30 minutes, I don't think we were going to be able to do all of it. So I did a little templating here, but we'll walk through each of these lines. So this first line here, system, is just initializing this actor system that we use for initializing Akka actors or Akka streams. We've got our execution context for futures. We've got our logger. And then for this example, we're not going to be using these two as much, but we're clustering is initializing Akka clustering so that we can actually have multiple nodes that join this application and are able to collaborate and communicate. And then sharding will specifically, I'll talk about in the next example more. And then I've got this Kafka helper that basically will just generate our sources, reading the data from Kafka, and writing the offsets back into Kafka. And we can actually just look at that real quick. So this is our source. We are creating this Akka Streams consumer. We're using a committable source. And then right here, we're actually deserializing the messages from just a string or a JSON serialization into our quote object. And then the very beginning of our stream, we're going to be processing this tuple, which is just our quote message object, followed by a committable offset that will be committed back into Kafka when we're done processing our message. So let's get started writing some code. So here we are. This is just some setup things, and this Kafka runner is just feeding the data into Kafka. So we're generating a bunch of simulated data right now that we're then going to read out of Kafka. And then this Mapkincat stream is our stream that our stateful stream that we're actually going to write. So step one, we need to take our stream and we need to group by. We want to make sure that each of our stateful Mapkincat substreams is only getting a stream of one company at a time. So the first thing we do is we are going to use this very simple group by. So different from some of your, some other frameworks, people think of group bys as kind of bringing things together, which technically it is doing, but in this case, it's actually creating a substream for each individual company that we're going to partition our data by. So here I like to think of group by as more like partition by. And so with our group by, we need a max number of substreams, which we're just going to set to 10. And then we're going to set up our kind of partition key. So we're going to go all the way down to this company symbol. So for Tesla, it's TSLA, I think. For Microsoft, MSFT. And so that's how we're actually going to partition this first data. So now with this, we've ended up with a substream representing each company that we're going to be working with. Next, we're going to actually implement this stateful Mapkincat that I was talking about. So stateful Mapkincat, we're going to use our curly braces, and we are going to set up the state that we actually want to collect. So I'm going to call it here quote window, W-I-N-D-O-W, quote window. So this quote window, very simple, is just going to be a list empty of quotes when we get started. So this is the state that we're going to be adding to. Each message that comes into this quote window will be applied to this quote window. And then when each message is completed, basically we have a input of quote window. We can apply new messages to it, remove messages from it, and then on the next message that comes in, that new quote window state will be passed through. So now what we have to do is we have to set this up so that we have our Kafka message that is coming into this Akka Streams operator. And just to make things simple, I will name these quote. I will split out our tuple to make things clear. So we've got our quote, and then we've got our Kafka offset. And with these two things, I actually have a little helper function that I wrote that will do some work on this quote window. But our new quote window is going to equal, in our quote companion object, we've got this function called update quote window. So we're going to apply the new quote as well as the old quote window. And then we're going to use a duration of just 10 seconds for this example. Oh, sorry. This needs to be a var. So now we've got every time a message comes in, we're going to add a new quote to our quote window. And then this update quote window will actually drop anything that is not within our 10-second interval. So that's all that's happening is it's just taking the most recent quote, removing 10 seconds from it, and then dropping anything that's outside of that window. And then next, we're going to do our calculate our percentage change. another helper function just to calculate the percent change in the window. And then we just want to pass these messages forward. And then we will pass forward a tuple that will have our percent change message, as well as the Kafka offset. Potentially, we could pass more messages, like a bunch of messages forward if we wanted to, but for this case, we don't need to. And then last, we will merge our substreams. So now we have one outlet that's just getting these percent change messages. How much did something change by? And then we're just going to, for this case, take that message in and then do something like if there we go, message dot percent change message percentage. If that's greater than 1, threshold alert. And then the last thing we need to do in this map is we need to pass forward our Kafka offset so that we know that we can commit that back into Kafka and we no longer need to ever process that message again. So with all of this, I will come out of presentation mode and we will run this real quick. So while that's, oh, there we go. Oh, of course, I forgot to fix some of these. So I will just comment them out for now. And we'll try that again real quick. So there we go. This might be a little small. But boom, we are consuming messages and not everyone is causing a threshold alert, but every once in a while we are getting these threshold alerts. So with that, I will stop this. We will do a quick back to slides so that we can go to this next model. And one more quick example that I think we can fit in before we run out of time is our trying to introduce actually a sharded actor into this pattern. And I'm going to throw one twist into it also. So what we're going to do here is we've got messages that are coming through the system. And Akka Streams has this really nice operator called map async. And map async will make sure that a message that comes in will result in a future, and that future will be completed before it's passed downstream. So that's what happens here. And we can actually send a message to our actor, whether it's on our local node or a different node. That actor can process the message and return an acknowledgement message. And only that message will only move forward after we get our acknowledgement back. So we're going to collect state in this actor and actually do our windowing there. But to throw another twist into it, that a tool that I really like to use in, well, it's just a very convenient tool to use in Akka Streams. So it's very easy to pass messages from streams into actors, but people can sometimes get confused on, well, if I just have an actor and I have a running stream somewhere, how can I put a message from that actor back into the front of the stream? And there's actually a tool called, or a source type called source.q that will allow you to drop messages into the front of a Akka stream. And so that's what we're going to do. We're going to have messages coming in, going to an actor, windowing an aggregate, and then that actor, when it hits this threshold, will offer a message into the downstream. And so jumping into that and coding this one real quick. This is that very cool stream operator I was telling you about, source.q. So this is going to create a stream that will, it's a normal Akka stream, but the result of creating this stream is this thing called a bounded source queue. The bounded source queue, you can just put objects into, like a queue, messages, and the source will process them. And so this actor is actually going to have a reference to that queue and be able to just put things asynchronously into that queue. And so we're initializing our actor sharded system right here. We have our sharded actor that I've already built out, the security metrics entity. This is going to accept messages of type quote, and then it's going to return an acknowledgement that says, I've processed this message. And then in its internal state, it's going to generate this window for us. And anytime it has a threshold that it's, anytime that the window hits that threshold, it's going to send a message to this queue we talked about. And sorry, I'll also mention each company gets its own actor. So each company is going to have its own actor that's started up by actor sharding. And so each company will have its own window. And so those actors could potentially do more than just windowing this basic information. So now we're going to do our map async. We're going to open up our Kafka message again, and let's try this again. Compiler is not picking that guy up for some reason, but not important. Kafka message. Oh, of course, I forgot the parallelism. So in our map asyncs, you can have different amounts of parallelism. So how many features do you want outstanding at any given point? So that's what we have there. So now we have our Kafka message, and we've got our quote, and then our second one is our Kafka offset. And here we're just going to get a reference to our, we'll call it the quote actor. We need to tell it specifically which actor we want to send messages to. And then we need to quote dot, and then which specific actor we want to get. So for this case, we're getting the actor that has this symbol. And so now this is kind of like a mailbox, like a specific place that we're going to send a message to. And as a message comes in for Tesla, we're going to go get the Tesla actor, send a message to it. And if I were to have multiple nodes in this application, these actors could be spread across all 10, 20, 30 nodes, and we would be able to still send messages across the network and then get our acknowledgements back in this exact same code. And then last, we're actually going to send the message to the actor using something called an ask. So an ask is going to expect a specific message type back. So I knew I wrote a couple things real quick right here. I'll just add a quick duration. How long do we want to wait for this message to come back? And talk through this. So right here, we've got our quote actor. We're expecting back a ACK message. And so, well, yeah, we're expecting back an acknowledgement. And then we're going to send this message, this quote message, to the actor. And then we're going to kind of sign it and say, well, here's how you respond back to me. And that's what this reference is right here. It basically is, once you're done processing this, send a message of type ACK back to this reference. And that's how sending a message to an actor works. It's very, very simple and easy to do. And actors are great ways to build applications. And so that returns a specific future. And we actually, down here in this Kafka sync, we want to give it back the Kafka offset. And so now, after this actor successfully finishes processing this message, we're just going to send that offset back to Kafka, and then we'll be done. And so that is all we had to do to send a message to an actor. And we will run this one real quick. And then do a quick 3-minute wrap up with this one other pattern that I absolutely love, but sadly I'm not going to have time to demo today. So, yep, this is our second example. And now we're actually sending these messages to the actor. The actor is printing out the percentage change, and then the actor is calculating the percentage. And then it's also saying, hey, we were able to write it successfully into that source.q that I mentioned. And then this is actually the message that was in that source.q. So we were successfully able to design this pattern right here. So map async sending messages to actors, actors sending messages back to Akka Streams. And so jumping forward into our last kind of model that I think people should be aware of in Akka Streams. So we had this example of, we're reading a message out of Kafka that's partitioned by symbol, and that message is being read out by node 1, but the actor for GM is always on node 2 right now. So Kafka and Akka are sharded in 2 different ways. And that means that every message for GM is always going to need to do a full 2 network hops in order to be processed successfully. There's actually a really great way built into Akka, specifically for Kafka, to actually co-locate or to use the Kafka sharding to also shard the Akka actors. So we can basically guarantee that GM will always be on the same node as the one that is assigned to reading that partition. And this is called Kafka cluster sharding. And so, well, there's a new tool called, well, I guess it's new from like a year ago, but it's a very cool tool. It's called the external shard allocation. So basically, Akka can rely on external systems to say, how should I be internally sharding my data? And the documentation for this is right here. And it makes sure that with these nodes clustered, we're always going to have GM reading off onto the same node as the actor is located. And if Kafka ever assigns this partition to be read by node 2, Akka will actually take that queue and also move the shard. So this example is in my examples. So if people want to have if people want to take a look at these examples, look at all the code, see how it all works, recommend going to, I've got it pinned on my Nolan Grace GitHub. So I'm Nolan Grace on GitHub. And this is the repo, so it's got all the built-out examples in it, including that final example. And for like my favorite person in the entire Akka Streams community for the content that he generates is Colin Breck, an engineer at Tesla. His blog is absolutely exceptional. It's helped me learn so many things, and I know I refer it to a lot of people who are also learning Akka Streams. So highly recommend taking a look at Colin Breck's blog. And with that, thank you so much for having me. I really appreciate it. And I'm looking forward to hearing from people in the Q&A.